Earlier, we were concerned with two principal characteristics of reservoir rocks. Firstly, storage space, that is, porosity, and, secondly, the ability of rocks to permit the movement of gas and oil. Let's talk about the second principle now. In particular, we'll talk about Darcy's law, one of the fundamental building blocks of reservoir engineering. Darcy's empirical flow law was the first extension of the principles of classical fluid dynamics to the flow of fluids through porous media. Its significance is that it introduces flow rates and timescales into reservoir engineering and relating these to pressure changes in the reservoir due to production of gas and oil. Henry Darcy was a distinguished engineer, scientist and citizen who is remembered for his many contributions in hydraulics, including Darcy's law for flow in porous media. While he's been given full credit for the finding, little insight has been available on the process of his discovery. However, his discovery was the logical result of a lifetime of education, professional practice and research. Darcy understood both the significance and its relationship to the broader fields of hydraulics and groundwater hydrology. Besides the discovery of Darcy's law, he was the first to show that significant flow resistance occurred within aquifers, the first to recognise the law of similarity to Poiseuille flow, and the first to combine the law with continuity to obtain a solution for unsteady or transient flow. When we talk about the ability of a rock to permit flow of gas, oil and water, we're interested in just how easily or difficult it is for fluids to move from one point to another in the reservoir and into a wellbore. How easily the fluids can move through a rock is determined by both the properties of the rock and the properties of the fluids themselves. The rock property which controls fluid flow is called permeability. So, we can say that if a rock is very permeable, it has high permeability, and fluids can flow through it easily. If a rock is not very permeable, it has low permeability, and fluids flow through it with difficulty. If a rock is impermeable, then fluids cannot flow through it at all. Darcy's original law, which was experimentally derived by Darcy in 1856, states that the volumetric flow rate through a core is proportional to the cross-sectional area to the pressure drop across the core in terms of gravity head and inversely proportional to the height of the core. Darcy's original experiments used a vertical sand-filled cylinder, shown schematically in the figure. In his experiments, the only variation was to change the type of sandpack, which had the effect of altering the value of the proportionality constant, but it did not investigate the effect of different liquids. The equation can be restated in terms of the difference in pressure between the top and bottom of the sandpack. For an inclined sandpack, Darcy's original equation remains the same, except that the flow rate is now inversely proportional to the length of the sandpack rather than its height. Instead of dealing with pressure directly, we can define a fluid potential with respect to some zero datum depth. This gives the volumetric flux in terms of the difference in potential between the top and bottom of the sandpack. The volumetric flow rate per unit area, obtained by dividing the flow rate by the cross-sectional area of the sample, defines the Darcy velocity. The Darcy velocity does not correspond to an actual physical velocity. It assumes that flow occurs across the entire cross-section of the sample. Flow actually takes place only through interconnected pores at the seepage velocity, which equals the Darcy velocity divided by the sample porosity. The seepage velocity is not the same as the interstitial velocity, which is the average velocity of the fluid flowing through the pores. Interstitial velocity is seepage velocity times the tortuosity. The tortuosity is the ratio of the length of the mean flow path to the linear distance. What is remarkable is that the Darcy velocity, which is the volumetric flow rate per unit area of the rock sample, depends only upon the hydraulic conductivity of the rock fluid system and is independent of porosity. Darcy's law, in its original form, is rather restricted in its usefulness, since the proportionality constant depends upon both the properties of the porous medium and the fluid properties. It would be expected that increasing the fluid viscosity would increase flow resistance, as shown in the video for oils of different viscosities. Further, as shown in the lower video, the flow rate of water is strongly influenced by the properties of the porous medium through which the water is flowing. The flow rate through fine clay is significantly less than the flow rate through sand. What is surprising, perhaps, is that the influence of the type of porous medium and the fluid viscosity can be separated and are independent of each other. In the following, we will see how Darcy's law was modified to account for this. In the 1930s, the proportionality constant in Darcy's law was extended by setting it equal to rock permeability divided by fluid viscosity, giving the generalized Darcy equation in its modern differential form, where Darcy velocity is proportional to rock permeability, inversely proportional to fluid viscosity, and proportional to the potential gradient in the direction of flow. The form of this relation is subject to the following set of conditions: incompressible fluid, no gas slippage, viscous flow, steady state flow, no fluid-rock interaction, and single-phase flow. In this form, permeability is intrinsic to the rock sample and, ideally, its measurement is independent of the fluid flowing through the sample. The standard oil-filled unit, termed the Darcy, is defined as the permeability of a medium that flows 1 cubic centimetre per second of a 1 centipoise viscosity fluid with a pressure gradient of 1 atmosphere per centimetre through a cross-sectional area of 1 centimetre squared. For convenience, the millidarcy, 1/1000th of a Darcy, is often used instead of the Darcy. Permeability has dimensions of length squared, and in CDS units, 1 Darcy equals 9.869 by 10 to the minus 9 centimetres squared, approximately 10 to the minus 12 metres squared, or 1 micrometre squared. The quality of gas and oil reservoirs with respect to permeability is shown in the table. Because gas has significantly lower viscosity than oil, a good gas reservoir has an order of magnitude less permeability than a good oil reservoir. If gas and oil are to flow through the rock matrix, then the pore spaces that contain the gas and oil must be connected together. The gas and oil must be able to pass from one pore to another. If the pores are not connected, even though filled with oil, as shown here, then no movement can occur. So, even a highly porous rock would be non-commercial as a producible gas or oil reservoir if there's no or little connection between the pores. Examples of these rock types include some chalk formations and some sandstones, where the pore throats are bridged and blocked by clays. The image shows an electron micrograph at 2 scales of an ecophyst chalk, dark its porosity, where the porosity of the sample is high at 28%. The permeability is very low, less than 1 millidarcy. Shown in the top figure is a thin section of sandstone with porosity 35% and permeability 866 millidarcy. The binary image has contrasted grain pore space using a binary filter. The bottom image shows a thin section and binary image of a sandstone with porosity 21% and permeability 110 millidarcy. The striking difference between the sections is not so much the reduction in porosity, but the significant reduction in connected pores seen in the lower permeability sample. Permeability is primarily a function of how well pores are connected. The figure, adapted from Freeze and Cherry, gives permeability ranges for both consolidated and unconsolidated sediments. Only sandstones, limestone and dolomite, fractured metamorphic and igneous rocks, permeable basalt and karst limestone are potential reservoir rocks. The characteristics of the rock determine whether permeability is high or low. If grains of the rock are large, as in the left of the image, then the pore spaces will be large. If the pores are connected, the oil will have high permeability and the fluid will move through the rock easily. On the other hand, if the grains are small, as in the right of the image, then the permeability will be lower. That is, there is increased resistance to fluids flowing through the rocks. As we have seen previously, the size of the grains does not affect porosity, only grain packing impacts porosity. Permeability, on the other hand, depends significantly on grain size and the distribution of grain sizes in the rock. The image shows the impact of grain size for a binary mixture of glass beads. While there is a slight reduction in porosity for the finer beads, due to imperfect packing of the larger beads, the reduced permeability for the fine bead packing, measured in experiments, was between 1% to 20% of the coarse grain permeability, depending on grain size ratio. Note there is a minimum of both porosity and permeability at some critical mixture ratio, which shows the significant impact of grain size sorting on porosity and permeability. The rock permeability appearing in Darcy's law is assumed to depend only on the rock itself, and, if the pores are completely saturated with fluid, the permeability will have the same value irrespective of the nature of the fluid. This is largely true under normal reservoir pressures and flow conditions, except for some aspects of real gas flow. At very low pressures or very low permeabilities, there is a slippage between the gas molecules and the walls of each pore, leading to an apparent increased permeability. This phenomenon is called the Klinkenberg effect. There are 4 regimes for gas flow in porous media. Continuum flow. Collisions between molecules are dominant, and the interactions between molecules and pore walls are negligible, and Darcy's law applies. Slip flow. The mean free path of gas molecules approaches the diameter of pore throats. The molecules slip along the wall and the velocity is accelerated. Transition flow. Transition from slippage to Knudsen diffusion. Free molecular flow. The molecules move independently of each other and collide with the pore walls more frequently than with each other. This usually occurs at very low pressure or in very tight pore throats. For reasons of speed and efficiency, gas permeability has become the standard for measuring permeability during routine core analysis. Because gas compressibility causes flow rate to vary along the length of a core plug, Darcy's equation is modified to calculate the gas flow rate at the average pressure in the core plug. This results in an equation relating gas permeability to outlet pressure, outlet flow rate, and sample length divided by the cross-sectional area and the difference between the squares of the inlet pressure and outlet pressure. Measured gas permeability needs to be corrected for the Klinkenberg effect. In 1941, Klinkenberg developed an equation relating equivalent liquid permeability or Klinkenberg-corrected permeability to measured gas permeability and the reciprocal of the average pressure. Taking a series of measurements at different mean pressures and extrapolating to infinity gives the Klinkenberg-corrected permeability as the intersection of the best fit line with the gas permeability axis. The permeability of a porous medium is isotropic if it is independent of direction, which has been implicitly assumed in the Darcy equation. Otherwise, it is anisotropic. The experimentally derived form of Darcy's law was one-dimensional. When the flow is three-dimensional, the equation generalizes to a vector form, where the Darcy velocity is a vector with the direction and magnitude given by the gradient of the fluid potential. This form of Darcy's law applies to homogeneous and isotropic porous media. In this case, the structure of the pore system is uniform and similar in all directions. The image shows coloured pressure contours of a pressure field in a square domain. The flow velocity vectors, shown as white arrows, are perpendicular to the pressure contours, and their length is proportional to the magnitude of the pressure gradient. In general, real reservoir rocks are neither homogeneous, that is, they are not spatially uniform, nor are they isotropic, that is, flow through the rock is not uniform in all directions. 4 examples of grain sign distributions and orientations are shown schematically in the figures. The sections shown are isotropic and homogeneous. The grains are uniformly random, with no preferred direction for flow within the section. Isotropic but heterogeneous. There is a clear trend in grain size from top to bottom in the figure, but no preferred direction of flow. Anisotropic but homogeneous. The grains are distributed randomly, but there is a preferential flow direction parallel to the long axis of the small elongated grains. Anisotropic and heterogeneous. Small elongated grains, which are often deposited in microlaminae, are oriented in one direction, with preferential flow along the direction of their long axis and reduced permeability transverse to their axis. In 1948, Ferrandon developed the tensor form of Darcy's law for anisotropic rock, which treats permeability as a three-dimensional symmetric permeability tensor. This tensor is more conveniently rewritten in terms of the principal permeability axes, where the permeability tensor has a diagonal form. The axis directions are referred to as the principal permeability directions, and the diagonal terms are the principal permeability values. For isotropic porous media, in which the permeability has the same value in any direction, streamlines are orthogonal to the equipotential lines. The flow direction given by the Darcy velocity is parallel to the potential gradient. For anisotropic porous media, in which the permeability has different values along each of the principal permeability directions, streamlines are not orthogonal to the equipotential lines. The flow direction given by the Darcy velocity is no longer parallel to the potential gradient. The permeability and flow in any direction can be calculated from the permeability ellipsoid, which plots the inverse of the square root of permeability in 3 space. The axes of the ellipsoid are aligned with the 3 principal permeability directions. Permeability anisotropy may manifest at all scales in a reservoir. Generally, the dominant impact is the ratio of vertical to horizontal permeability, the kV/kH ratio. Vertical permeability is usually significantly lower than horizontal permeability with respect to the plane of the strata, due to thin laminae arising from initial sand deposition, as shown in the radiographs on the right. At a larger scale, there may be significant permeability contrast between different layers or stratigraphic units, or permeability anisotropy within a reservoir layer. The middle image throws sea cycles of deposition and erosion of Aeolian dunes in the Navajo Sandstone, Utah, with permeability anisotropy between a flow direction perpendicular to the cross-sets, the direction parallel to the cross-sets, and vertical permeability between layers, which is influenced both by the cross-sets and the permeability of any thin sands or shales deposited between the layers. The bottom image shows iron oxide precipitation around fractures in sandstone, Hokianga, New Zealand. Such precipitates and fractures and joints can significantly reduce transverse flow. On the other hand, open fractures and joints may enhance effective permeability parallel to the fracture system. Permeability anisotropy can arise at a macro scale due to the depositional environment. In particular, cross-bedding within a reservoir unit and microlaminations parallel to the paleo flow direction. In the example shown here, a fluvial system has a maximum permeability within channel deposits in the direction of paleo flow. Macroscale lateral and vertical permeability is reduced due to the presence of clay drapes, bar surfaces, and other fine-grained mud deposits. The images show the development of fractures related to structural folding. While fracturing in folded areas is often complex, the main extensional fractures, in this example, run parallel to the fold axis. In many cases, these fractures are open and enhance permeability along this axis. However, if the fractures are healed and filled with cement, then transverse permeability can be reduced. In either case, significant permeability anisotropy is present, with the maximum permeability along the fold axis, with reduced permeability in the dip direction. Okay, we've had a brief introduction to permeability and Darcy's law, which is the cornerstone of reservoir engineering, and in particular, reservoir simulation. We'll look at applications of Darcy's law later. As we've seen, permeability is an intrinsic property of a porous rock, and for single-phase flow is independent of the fluid flowing through the rock. Its importance is that it relates the volumetric flow rate of a fluid to the pressure gradient driving the flow. For a fixed fluid and pressure gradient, volumetric flow rate is directly proportional to permeability. We haven't looked at the relationship between porosity, permeability and different rock types and facies. We'll discuss these topics once we have studied capillary pressure, which follows the next section, Part 4, Reservoir Fluid Properties.